Well, good morning, everyone. First, I'd like to thank the organizing committee for inviting me across to speak at your conference. I hope that what I have to say will be of some interest and value to you. Just a little bit of background. I'm semi-retired. I work at the Atomic Weapons Establishment in the United Kingdom. We actually produce the nuclear warheads that sit on our submarine ballistic fleet. By training, I'm a physicist, although I've got at least one leg on the engineering side, so I understand both the science and the application side of technologies. Let's see, what shall I say next? Because I work in a very high consequence industry, most of the work relates to the balance of advantages of AI versus the risk that it poses. And in this case, in the technology I work within, the risks are quite high, or the consequences are quite high. So we are very cautious about how we apply this technology. And to some extent, we don't apply much of it to the designs that we're involved in or the processes by which we manufacture our products. So that's what I want to speak about. Some historical aspects, biological intelligence revolutions, industrial revolutions, safety warnings, visions of the future. Can machines innovate? The general concerns, and then in the second part, talk about safety standards. By safety standards, I'm not going to say what they should be, but rather the areas in which we need to have safety standards. So historically, a continuous race between the implementation of new technologies and the development of appropriate levels of safety and regulation. So it started with the Industrial Revolution, progressed to the widespread application of microelectronics, software IT. Now we are entering the realm of artificial intelligence and the moves towards machine-based decision-making or machine-based support to human decision-making. It's at a relatively early stage, and there are always concerns that the supporting research into safety isn't keeping pace with the application of AI technology. So I'm suggesting there's a need at the moment to identify a set of new safety standards, and especially those are required if you're involved in high consequence operations. So this talk is going to give a broad brush approach to the subject. So Max Tegmark, he's the president of the Future Life Institute, and his concerns are about where biological evolution will get to in the future. And he's identified 3 epochs. The first one starts at the single-cell bacterial level with some ability to cope and understand how it contends with the environment. And through that will gradually evolve into a new and changed form. The second epoch really centers around how we are today. Basically, the improvement today is much more based on being trained, having access to technology. So we're not in the position of major biological changes. In fact, if we look through history, our forebears were monkeys far enough apart. If you go from that stage to where we are today, We haven't changed an awful lot. Our heads are slightly bigger, the brains are slightly bigger. What we don't foresee as we go towards Epoch 3 is the fact that humans are going to change biologically and have heads which are 10 times bigger than what we have at the moment. So Epoch 3, that's broadly associated with the realm of superintelligence, where machines now surpass human capability to perceive, decide, act where humans control, and on the face of it humans play a smaller and smaller role. So there are threats in relation to loss of human control. There could well be an explosion of artificial intelligence, and we may see a quantum change in the world we live in. And so I'm going to talk about some of these things in the first part of this talk. Okay, so in parallel with that, there are a number of technology revolutions. I will list three. Perhaps it started with the agricultural revolution, but I'll start with the industrial one. That enabled us to use fuels like coal, oil and gas to generate steam, to enable us to perform certain operations we couldn't before and produce products we couldn't before. That was very much human-maintained safety. There were always humans in the loop. There was always transparency in that even a non-expert could see how these operations were performed. They were never complicated and not tightly controlled. This was very much about an era of human control and transparency. The next revolution, well, that's the IT revolution. It was no longer transparent in the sense that control was now bound up with software which had special languages, special lists, and only the expert could understand what those lists were telling you. It was implemented by a web of interconnected, very small entities with no outward indication of what they did or how they worked. But that revolution was still very much about human control of safety, including the need to develop new safety standards and methodologies to meet the loss of transparency and the increase of complexity that occurred. The process was still generally rule-based and applied cause and effect. So there was always an understanding of why something caused something else. So there was a goal for a perfect specification, and hopefully that would lead to a perfect implementation. And there were many attempts to do that in a mathematical form, so that there was an absolute mathematical transfer from the specification to the application. That never succeeded, and in fact confidence was achieved through, which was pretty well brute force testing, and the so-called SIL, Safety Integrity Level approach to certification. So technology revolution 3, well, we've got automation, which is already with us, and AI is sort of growing very rapidly. AI is now beginning to solve problems more efficiently than problems that we couldn't solve in the past. And examples are chess and the game of Go, how now targeted artificial intelligence is able to surpass the capabilities of humans. But the complexity, well, for instance, there's an example there of how it relates to the human brain, which is 100 billion neurons and several hundred trillion synapses. So when you're thinking of artificial neural networks, you're beginning to look at AI comparisons with those capabilities. Unfortunately, the complication in machine artificial intelligence gives further problems in lack of transparency about cause and effect. You're never sure quite how the machine makes its judgment. We still haven't got to the position where we can look into the machine and say the evidence shows it makes good judgments, but we can't still trace the cause and effect logic which gives rise to that. And basically, we are in the realm of deciding of how we allocate control and decision making between a machine and the human. And what I'll do here is just to let you read some of the warnings that have been issued by luminaries in the subject area. Perhaps I'll pick out two. Alan Turing was probably the first one to raise concerns about machines and if they become more intelligent than us, the dangers that could ensue. He also said that you can always turn the machine off if you're concerned. Of course, the counter-argument to that is the machine has already sort of anticipated its survival in those terms. Alan Turing was famous as a secure part of the grouping in the UK that broke the Enigma code during the Second World War. The Enigma code was the German military coding device which passed over the military messages. And also it was the birthplace of the first electrical computer, an analog computer. I think it was called Colossus. And the one below it has some geographical relevance. Where Elon Musk has suggested that artificial intelligence can bring forth even bigger concerns than the risk of North Korea. I mean, I hope there are no North Korean personnel in the audience. I don't wish to be disparaging, but... And in fact, Roger Penrose, who's a famous mathematician and philosopher at Oxford University, has a much less pessimistic view for the future. His view is that AI machines will have much more limited ability to map their own futures. And so he's trying to allay concerns that we're not going to sort of end up in a machine world where we are in dire concerns. So a vision of the future, well, I don't think there's any clear indication of how far AI will go. There are concerns about, as it becomes more complicated, there's the parallel problem of a lack of understanding of transparency of how it works. Machines, in principle, could become self-learning, self-testing, and self-designing for the purpose of continued intelligence capability enhancement. In turn, it's possible that AI machines will develop their own goals, their own self-interest, inter-machine collaboration, which may be in conflict with society's interests. And the question that arises, can humans retain control to prevent this? And then, of course, in the worst case, could it lead to a machine society with all the human characteristics of self-interest, competition, aggression, and even direct conflict? And people talk about the singularity principle, where AI has accelerated so quickly that humans no longer play a part in forming or even understanding the world they inhabit. All of this is sort of very futuristic and may not happen, but a number of people have really sort of compared this with global warming, in the sense that global warming, the real problems haven't occurred yet. But if you're going to solve that problem, you need to act in advance. The same applies to concerns about machines in the future. If you can see at this stage there are possibilities that machines will get into a position which will be out of kilter with human interests, then we need to understand these possibilities and to look to possible solutions to prevent it happening now and not when the problems occur. So how far will AI go? If I talk about hardware aspects first. So we're comparing that with the human brain. Again, I say 100 million neurons, several hundred trillion interconnections. And we still don't understand how the brain operates in such a massive parallel processing manner, and how it builds up its own internal algorithms which control that process. But when you look at modern IT machines, then they've got a lot going for them. Modern computers run at the gigahertz speeds. Neurons in the brain, they have a speed of about 200 hertz. Modern computers transfer information with roughly the speed of light. In the brain, it's traveling at roughly 100 meters per second. Modern computer RAMs are much bigger than the suggested memory working capacity of the brain, and similarly, modern computers have much greater memory storage than the brain. Also, there is no limit on the size of a modern computer because it transmits information at the speed of light. It can be as large as you want. Looking into the future, we don't see our heads growing without any limitations. So the suggestion there is that there is nothing to prevent AI machines competing with and surpassing humans in the future. Hardware developments, well, currently switching elements in computers are typically a few atoms in size, and even if you're storing information, you're down to individual particle sizes. For instance, you can store information in terms of electronic spin up or spin down. You've got two possibilities for the position of that electron. One of the problems that occurs is that as AI machines become more complicated, the algorithms which control them grow in exponential complexity. And Richard Feynman, who is a very famous American scientist, he's made that statement: if you want to solve a problem of quantum level of complexity, you need a quantum computer. And in fact, if you look at the literature, there's already evidence that people are using quantum computers and quantum algorithms in machine learning processes in order to solve quantum level problems which have been out of the reach of standard serial related algorithms. And I'm not sure if I'm up to date there, but the leading quantum computer at the moment is a Google Sycamore. It's got 53 subatomic, these electron entangled qubits. The issue there is how to build these big machines and keep them isolated from the external world. The external world interferes with the qubits and as such destroys the entanglement properties of the machine, and that gives rise to noise error corrections, and that's an area of fundamental research at the moment. Software, I think all I would say there is that there appears to be, in principle, no limits to what one can do with the software. There are no physical laws which prevent that. But again, the problem relates to the complications of the algorithms with normal computing machines. And there's, in principle, going to be... it looks as if it's inevitable that in the future, artificial intelligence will move into the quantum computing world, where their quantum computers can manage vast amount of parallel processing because of the qubit nature of the individual elements in the machine. An interesting issue there is, can machines innovate? After all, in a human, the information sits in our minds, and obviously there is some instant where somehow or other we brought that information together in a form which allows us to produce new ideas, the so-called switching on of the light bulb. The question is, will machines ever get into that position? And again, if I raise Roger Penrose into the discussion, he thinks that will never happen. Machines will have a limited targeting goal for their purposes, and as such, they won't have the freedom that humans have to employ this wide-scale targeting of innovation. He thinks there are fundamental differences between the two. Some typical current safety concerns. Well, I've listed the MCAS, the 737 MAX 8 there. I'm not sure how much that relates to AI, but obviously they didn't get that right, and it led to, as you know, to crashes of that aircraft. The quality of the learning and testing processes prior to full application, that's obviously a concern. Obviously, the quality of the AI statistical analysis and confidence levels associated with outputs. AI is not a deterministic science. Basically, it all rests on distributions, uncertainties, and confidence levels. And also, we will, until we get a better understanding, we will always have concerns about the transparency about AI actually arise of its decision making. In that sense, we need a process analogous to the current SIL approach to microelectronic safety, and that is to establish an auditable, evidence-based assessment process which is matched to the potential risk and consequence level associated with false machine outputs. So back to the here and now, we need new standards, we need new safety assessment methodologies. And as I said, I'm not going to suggest what they are, but more to point to the areas where they're needed. So the first thing you need to think about is the risk-benefit analysis. Whether to use AI in the first place. What advantages does it give you? What risks does it impose? And what are the consequences of those risks, which if you get it wrong? As I said at the beginning, because we work with a very high consequence industry, if you look at that balance scale there, the risk and consequence element of the balance weighs very heavily on us. So we are very, very cautious about applying AI to the design of our products or to the processes by which we produce them. And again, you have to look through the quality of the artificial neural network structures, the quality of the training sets, quality of the test data, the validation and verification of the control and statistical confidence algorithms, the monitoring of programs from anomaly detection, recording, sensing, and correcting. That means when you're running AI for real, you need to keep an eye on it to make sure that it continues to do the right thing, and if it doesn't, to react accordingly to that. Also, the issue of independence will crop up in the use of artificial intelligence. Totally independent AI machines, either operating in a peer review or controlled manner. Peer review is that if you had 3 machines, do any 2 agree with each other? Or in control mode, there are even suggestions that you have an operating AI machine and a supervising AI machine which continues to look at the output of the first one and has special properties to make judgments to either stop or question the outputs from the first machine. Obviously, even for, independent machines, you can have independent constructions and algorithms, and those machines can have independent training and testing sets. So those are all related to maintaining the idea of independence if you're going into the realm of AI machines for either designing or carrying out some of your processes. So in the structure of a neural network, obviously you have decisions to make on the number of neurons, their layers and the interconnections. Obviously, the more complicated you make it, the better precision you will get out of it, and the lower the uncertainty of the outputs. But that does produce increased cost and effort during the training and testing processes. And certainly over-complexity can lead to overheads in computing and more loss of transparency, and sometimes you can end up with complication giving you even poorer results than a simpler application. The training set should be compatible with the machine input interface. That means that's just good shopkeeping, that what you're putting into the machine is what the machine understands what is being given, that you don't have a problem at that interface. Should be complete, comprehensive, accurate and balanced. The training set should be sufficient to cover all of the expected input conditions expected during final application. So you really need to look at all the scenarios that machine is expected to encounter and train the machine against all those scenarios. There are concerns obviously about input bias. I'm not talking about malevolent bias, but we're all subjective. So if you train a machine, the machine is going to take on some of the characteristics of the person who trains that machine. So we want to make sure that we go through processes which are as independent of human bias as possible. And I think in your last conference, Mr. Stuart Reid spoke about some of those bias problems. I've just put that up because I think you will recognize some of the errors that have occurred and reported during the use of AI application. facial recognition, false identification, healthcare diagnosis leading to wrong treatment, and I'm sure your next keynote speaker will say a little bit more about that. Gender bias in job application, race bias in prediction for potential law breaking, poor business decisions, stock market crash, automobile malfunction leading to death or injury. And I think the introductory speaker has already spoken about that totally autonomous cars are not perfect as of yet. And the last one I've got here is a sort of artificial intelligence. Apparently, before the last World Cup, I think it was an octopus was exposed to various characteristics of the teams that were going to take part in the World Cup. And from that, it made a prediction of who was going to win. Of course, it got it completely wrong. Does anyone in the audience remember who won the last World Cup, football, soccer cup? No? France. So all I would say about the test data set is that it will need to have all the same requisites that the training set does have. The danger there is that most often than not, the test data set is really a subset of the training set. So if you've got a bias in the training set, it's likely to be carried through into the test set. So you really need to be very careful that that if you put bias in at the start, you're going to sort of see it carrying through. Let me go into the next one. Application. In application, the process continues with improvement. So once you're applying AI, it's a process of continuing monitoring the output and the accuracy of the output and the errors that appear. So you're into the issue of the level of monitoring. How carefully do you monitor the system? The level of anomaly discrimination and mitigating response to those, identifying the causes of anomalies. And there is such a thing as output bias. And if I can give you an example, there are some people back at AWE who've been using artificial intelligence to classify documents. Basically, a certain comment on its own, by classification I mean security classification, comment on its own isn't classified. But if associated with another comment, when you put both together, you do change the classification. Now the AI was correct in identifying documents that should be classified, but it also appeared to classify documents which were unclassified as classified. So these people have had to look back into the machine and try and understand how this is so. And what's happened is the machine had identified that usually when two of these inputs occur together, they tend to be related to long sentences. So the machine decided I will also look for long sentences and not necessary for the individual elements that relate to classification. If I see a long sentence, I'll automatically classify it as classified. So what I'm trying to say there is that even if you've done a perfect job on the training and testing, the machine itself internally could generate its own biases, false biases. And the last comment is that if you intend to use the machine for a slightly different purpose, you have to be careful to ensure that the training and testing you've put it through is still appropriate for the new application. I think the last thing I'll talk about are the algorithms, which I think it didn't quite, the equations didn't quite come out as they should, but doesn't matter. There are two types. There's algorithms which look for minima in comparing the input to the machine, the correct input to the machine, and what the machine thinks it is. That's a world of mathematics which requires validation and verification to make sure that all is in order there, and there are very strict standards for getting those right, including, again, independent checks for bias, and again, sort of noting concerns about lack of transparency. The second class of algorithms relate to the confidence in the decision that the machine makes. What I've tried to draw there are symbolically two distributions. The left-hand one basically gives the probability that you've identified a safe state. The right-hand one is another probability distribution that you've got an unsafe state. Ideally, you want those distributions to be totally separate. But in the real world, those distributions tend to have overlaps in the tails. If you're dealing with a high consequence industry, then the area of that overlap is very important. For example, in the nuclear weapons world, we look for a confidence level of 1 part in a billion per year for the safety of the device. So you can see how concerned we are about tracing those tails to make sure that if there is an overlap, the area in that overlap pair of distributions is exceptionally small. And I suppose finally we're always left with the transparency and the black box syndrome. The process appears to always be making the correct assessment so far. But is it still really based on solid foundations? Because if you don't have a cause and effect understanding, can it still put you into a very difficult position? And I think I'm just talking there about the black swan syndrome, in which there's something you hadn't thought about, which suddenly turns up as a low probability, but it turns up, and it's a tragic event. I tried to put a black swan there, but the best I could do was a black duck, I'm afraid. So, hence the requirements for high levels of scrutiny in the processes of training, testing, monitoring, and the V&V of the associated algorithms. And certainly at the moment, there's a real need for more research into cause and effect rather than simply brute force testing of the machine telling you that it always comes up with the right answer. And you need to do that to gain more confidence. And I always suggest that if you are making a safety case for the application of artificial intelligence, you don't make it solely on the fact that it appears to give the right result with a high level of confidence. You also need to have some evidence of understanding of the cause and effect logic that sits underneath that. So, if you're going to have a set of standards, I suggest that they're going to mirror the current safety integrity level methodology, a rigorous evidence-based, structured and transparent confidence risk approach. And in the UK, we talk in terms of a safety case dedicated to the objective in mind, which links directly to the safety standards you're talking about. And that would include a detailed audit trail covering the supporting evidence from the structure, training, testing, execution, and algorithm validation, verification processes. And on top of that, at least some supporting evidence of an understanding of the cause and effect with which the machine appears to be effective in making the right conclusions. And I'm not going to go through there. What I'm going to say there are three groups of people who should be interested in this. Those who are proposing to apply artificial intelligence, those whose job it is to regulate, because the regulators eventually will set those standards, and they will look to the people who produce AI equipment that those standards are met. And thirdly, there needs to be a very healthy research activity which is very much concentrated on understanding the safety side of IA intelligence, and also to probe into the machine to get at least a qualitative, if not quantitative, understanding of how the machine does make its decisions, not just a case that it appears 999 times out of 1,000 that it makes the right decision. You really want to understand the logical basis behind that. And I think that's the end of the talk. So thank you for your attention and any questions.
네, 여러분 큰 박수 부탁드리겠습니다.